Okay. I think probably we should do more exercises before going, too far. So today's topic is still about streamer protocol. Let's just revisit a different version of streamer protocols that we understand the basic ideas. And I will examine more about some questions that people ask me frequently, especially first of all the commitment part, and secondly because there are only 3 steps in the Schnorr protocol. But so why 3 steps? Why, and each step, what's the reason or idea behind? All right, let's revisit the Schnorr protocol. We will have 3 or 4 different versions of. We can compare them, trying to you can probably get out some ideas. Okay, revisit Schnorr protocols. Okay, number 1, the original Schnorr protocol. And I also give some examples of call this protocol to prove something. Okay, for the original Schnorr protocol, there are a prover and a verifier, Alice and Bob. And the prover has a secret SK. Okay, from a prime field FP. Okay, P should be very large. And the prover will, before the protocol, the prover will commit SK as a capital K, and send the capital K as a public key in many applications. Prover send the key, capital key, to verifier. So verifier now has the public key, trying to verify if prover is the Alice, someone called Alice. So SK is the so-called witness. Okay, witness is another word of a secret, so can never be known by verifier. Otherwise, a verifier will be able to impersonate Alice. So, okay. The basic idea that is, how can verify the prover has SK without knowing what SK is. The idea is that we use the additive homomorphism of the thread bracket notation. So last session we introduced the one of construction of the bracket notation as a exponentiation operation over a finite field. So now we'll just give a concrete definition of thread bracket instead of abstract ideas. So I guess probably we have the concrete definition will be easier for you to understand. So we'll have a G to SK. SK is just one number, and the G is a generator of a finite field of P, the multiplicative group of P. G is the generator, a generator. G is public. Public is a parameter of this protocol. And G to SK, the operation has additive homomorphism. Okay, let's let's check the property. Okay, here. So first we'll use the square bracket notation. So additive homomorphism is that we have A and B, A plus B equals to A. Okay, here. Okay, let's use plus here. We'll explain the subtlety. Now we use the concrete definition here. So here is A G to A plus B, right? The right hand side is G to A and G to B, right? All right, the subtlety is that here should be a multiplication instead of additive. Okay, probably, okay, this can be very confusing, right? Okay, here's the thing. Because the G to A or G to B, another two elements, are elements of a group, in a group, for any group, whether it is a multiplicative group or additive group, there are only one operation on that group. So formally, we will see definition in a mathematical textbook or abstract algebra book. They call the operation as the so-called the group law. Okay, the operation is just only one operation. So we don't have to distinguish addition and multiplication because there's only one operation. Here, for G to A, this group, all G to A, all kind of these elements form a group. So there's only one operation on that group. It is multiplication. So because there's only one operation, it doesn't matter that we use a dot or a plus or O plus or something. Just a notation, right? We can use any notation that we like to denote that the group law, the only one group operation. Okay. So I think, yeah. Here okay, this notation is my favorite, but kind of confusing for beginners because, but in the traditional academic papers especially from career graphic community, they prefer to use the traditional one, the multiplicative groups. But for the articles from crypto, from blockchain community, we probably like to use this one because in practice we always use the elliptic curve as the concrete definition of square bracket. But on the elliptic curves, there is such group law called addition. So that way we always use plus addition instead of times the multiplication. But right now, okay, let's just use this one, okay, because it's more consistent with with our high school math. Okay. Now we just use the G to A, G to B. Okay. Here is the. Okay, let me. Okay, here is the group law. But now we can see, okay, it's a sort of homomorphism. Usually we call it additive homomorphism. But I think multiplicative homomorphism, okay, the concept is okay, it's fine. So Okay, let's go back to Schnorr protocol. So any question about this part? No? Okay. Is it clear? Okay, if you have any questions, please raise your hand and or stop me. So let's come back to the Schnorr protocol. The basic idea that how the verifier can verify that the prover has SK without saying SK. So the idea is that we put SK into box. Here we just put into a G2SK, or put it into a box. And assuming the box to be right, because already the verifier has capital K with SK inside. But okay, so the question now is right now. So can verifier be convinced that prover knows SK inside the capital K? Can the verifier be convinced? Or imagine that you are the verifier. Convinced? No. Why?
Like we haven't done anything, right?
Yes, yes, intuitively, yes. The prover can pass capital K to everybody, right? If somebody just show capital K to me, so I'm not convinced.
Verify it,
Yeah, so the verifier had to do something.
To be a challenge.
Yeah, do some challenge to test whether P has something, has this. Otherwise, the prover just pass capital K to everybody, so everybody can be Alice. Okay. The idea is that, okay, the prover should encrypt the SK. Encrypt the SK by using the challenge from the verifier. Encrypt the key, the SK, and show the encrypted data to verifier. And then verifier will verify whether the encrypted data there is SK inside. Okay, not the, encrypt, not a boxed SK beforehand. The encrypted data must have something, challenged by a verifier. So this is the basic idea of Schnorr protocol. So first of all, the prover should generate something, as a symmetric key to encrypt SK. So let's use the notation R, the small r, as the symmetric key. Symmetric key for encryption. So this key is for encryption. Okay, for encryption. And the prover should send the R, capital R, the prover put the R into a box. Here we use the G2SK, G2R to the verifier. Then verifier will reply with a challenge C. Now, prover, according to the protocol, will encrypt the SK. Okay, encrypt the SK. Let's call it Z, as convention. Z equals to R plus C times SK. Okay, it's an encryption. It's an encrypted data, encrypted key. Encrypted key, but has a challenge inside. So that's why interactions matter, right? To show that, okay, if prover does not have a does not have SK. For example, a prover just asks my public key. The prover cannot do this stuff, cannot do this encryption. So as the last step, the prover just sends Z to verifier. So right now, if you know the FHE, for example, fully encryption, fully homomorphic encryption, that a similar idea that the verifier will homomorphically verify if the encryption is correct. Right? Z is the encrypted key. So the verifier will put Z into a box, like a capital Z, equals to GZ. Okay, put it onto a little curve, or put it in a box. So either a metaphor you can use to trying to draw a picture in your mind. So verifier will put Z in a box, then will homomorphically verify if this equation is correct. So sorry, capital Z equals to, now verifier in the first step already get R. R is like G to R, and times K, capital K to C. Okay. Three components are all the elliptic curve or points or the group element. Okay, let's use the group element. Okay, there's a group element, group element, group element.
So it's to the power of C because the multiplication in the field is the power in the group?
Yeah. Yes. Can you imagine that we have, for example, the world now on the ground, here is the sky, and now the prover calculates Z equals to R plus C times K, and each component has a corresponding component in the sky. Now I have Z, right? Z. R has R, and as K, capital K, right? Here we use the group law. Here's group law. So verifier cannot get all the details on the ground. What the verifier can only do is just observe or look into the group element, which is like like a mirror or counterpart of this field operations. Okay, but here, because we use a multiplicative group as the square box, so here we use. Okay. If we use a little curve, we'll use totally different notations. But I think use this notation, we will have a solid ground that we can easily calculate on paper to verify. No?
The inverse of the forwards. Yeah.
Why?
Times the scale equals capital K.
Because okay, why there's a exponentiation, right? That's the question, right?
Yeah, that's the question exactly.
Okay, because let me slow down. Okay, the group equals to G20, G21, G22, blah blah blah, all the way to G2P minus 2. That's each of those is an element from the group. And the group will have the only one operations. For example, if we H1 for all H1, H2 from group, we can have okay, like right. It's called the group law. And we can have such like the scalar multiplication, or a scalar multiplication, like that we're doing is C n times h1 equals to some h4. Why? Because n from an integer. N from an integer. So, okay, n times h1. Sorry. So h1 to n means that there's n number of h1. We have n h1 to multiply them together, get a sum h4.
Why h4?
For some h4. For some.
It's whatever.
Is there any? Is the result of
H1 is sure variable.
Then it should be hn or not h4?
We don't know. For example, if h1 is g1, then h4 is hn for sure. But not exactly. For example, if h1 is g2, yes.
H1 is not g to the 1.
It's for some h prime, If let's give some example. If h1 is g to 2, then h prime equals to g to n equals to g to 2n. Okay. Okay, just because the group elements, the group is a multiplicative group. So the scalar multiplication of elliptic curve actually is the explanation operation here. I'm not sure if any of you are familiar with elliptic curve operation or. Okay, just get used to the exponent part. Okay, scalar multiplication on multiplicative group actually is exponentiation operation. Yeah.
What is up to GP minus 2, no GP minus 1? Like the group, the last element of the group, the last
Here?
element, the last element of the group.
Okay.
Yes.
Because we only have p minus 1, the order of a group because equals to, and the order of a group is p minus 1. Yeah. So if g p minus 1 will be equal to 1.
What is the star?
Star is a multiplication. It's a notation from the mathematical guys. Yeah.
It's a multiplicative field.
Yeah.
Okay.
Yeah. Or formulate multiplicative group of the field.
If you try to write the equation, you will understand because that's what I.
If you try to write it like derive it.
Yeah.
Okay.
But I just needed to start to write it, and then you.
Yeah, it's a good idea. Write those equations yourself on paper. Yeah? Easy to verify. Okay.
I have another question. I'm wondering if there must be to C multiply sk, kind of like C plus sk, like I could say.
C plus sk.
Yeah. Can we do that?
No.
Zero yet. From my idea, I think we can also do that, but
You can try. You can write the protocol. Yeah.
Let me try.
Okay, can you write it here? Yeah, to this step. Okay.
Yeah, so like the first step is I will give a R
Mhm.
and he give a C.
Mhm.
This time I give C like just
R plus C plus SK.
SK, and so this will be equals.
Okay, very good, very good. Good job.
Um, C because it's provided by the verifier, so he knows C, and we can just keep it, and this will be SK. So
Okay,
in
okay.
this case, R is known by verifier.
Okay,
SK
okay.
is known by
It's
verifier.
not a scale, it's scale, right?
It's the K.
Capital K.
Yeah.
Right.
And from my opinion, I think it also
Works. Okay, okay, good.
Okay. But then you could divide by the other part and extract K?
You can't because the R verifier don't know what small r is, so he also
Okay, let me take a picture.
cannot extract it. But I think maybe multiply has a stronger hiding.
Yeah.
But I'm not sure. Can you? So yeah.
Okay.
Did you?
I love this class. Okay.
It's the same.
Okay. Okay, the challenge for you. So can anybody attack this protocol?
I have a question.
Okay.
We've been multiplying C with SK so long. Why are we adding up now?
Sorry, can you repeat?
We've been doing R plus C multiplied by SK.
Yeah.
Why did we change to addition instead?
It's his idea.
Oh, it's the idea. Okay.
Yeah, the new protocol, yeah.
Oh, okay.
And now we're just looking if we can attack this to show that it's.
Yeah, should is yeah, okay. Do you have an English name?
Mark.
Mark, yeah. Mark just showed us a completeness, a protocol with completeness. But I will encourage you to try to attack this protocol. So is there a way for a prover to forge a protocol, forge the proof without knowing SK? Okay, we can stop here for. Then we can understand why we should use times here, and what I mean by using multiplication here. We're not A plus. And Mark, very good job, very good job. Your thinking is valuable. Okay, so now, okay, it's a quick quiz. I love this class. Okay, repeat the new protocol is different from Shannon protocol that here we use plus, not a multiplication. So, is there any way for prover to forge the proof?
But there, I understand it says like box set is G2RCSK, or is box set R plus C plus SK? Because in the arrow is sending R plus C plus SK, or is sending G to the R plus C plus SK?
I think it's just sending R plus C plus SK.
Okay, so box
Yeah,
set.
yeah.
Okay. So that's
Yeah.
capital set. Capital
I
set.
think it's a small c, right? As the protocol. Yeah, small c.
Yeah, but I mean, like the sum is capital set. There is capital set G to that sum, because in the right it says box offset. In the right it says like it's saying there is.
Come here, Leo.
I don't think it's capital Z. Like this
So
one.
we are sending. Are we sending this or are we sending this?
I'm saying this.
Okay.
This.
So the
Here
box offset is.
It's
not this.
done by the verifier. Okay, but this computation is done by verifier. The verifier will
So we are sending lower cap set. We are not sending capital set.
Yeah,
Ah.
yes.
Should we
You guys get the result? Come here. How to attack? Yeah, come on.
No.
Your question?
I wanted to approach, like, I will approach with a field, and I will approach with a field with, like, maybe hit and trial or brute force to come up with a C, since C is an addition now, like in that.
Okay, yeah.
You mean at the end of the C can be calculated?
No, not calculated, like maybe just brute force. I don't know.
Okay, if the P is very large, you cannot brute force. The P is large.
Yeah,
Yeah. So think about the simulation, okay, that we talked about last Friday. So if you miss,
in the addition part, like we are not binding the challenge with the secret key.
yes, yeah. How to? My question was how to attack this protocol. Yes, correct. The C, yeah, we're just trying to figure out why multiplication here matters. Why, if we change the multiplication into addition, so what will happen? Okay.
You can probably negate the.
I just try it. Come on, you're close. You are very close.
No, I'm not saying that. I mean, we can probably somehow negate sk to the other side, so we can then derive something that we otherwise wouldn't.
No, it's close. It's close. You're close.
I don't know how to do that.
Okay, here's some hints. So here, why we use multiplication here? Because to the verifier, C is looks like a interdeterminate. In Chinese, the 未知数, something unknown to the prover before the challenge, right? So we can write a polynomial here as R plus sk as the coefficient times the ax. So it's from a math terminology. We have a vector space. We have some basis as 1x. The basis means that actually sk and r are on the different dimension, the coordinates. They are orthogonal with each other. So if we modify R, we cannot, will have no effect over the SK. They are orthogonal. But if we use addition here, R and SK on the one dimension, that will we enlarge R by 1, then we can minus SK by 1 to make sure that some of them is still equal. So still we can pass the verification, but actually we can, right? Did you get it?
Yeah, makes sense.
Okay, just come up with some attack to this protocol. You do it? Okay, come on, just write the attack. Just write the equation to attack the protocol. I don't know. I don't get. I don't get.
这个 C 不是 verify
Yeah, yes.
那么我这个时候 verify 肯定是知道他给我的这个东西的这个 R
这个东西是什么？这个东西。
小 R 是算不出来的。因为你不知道小的 S， you don't know the private key, so you can't derive what R is.
Okay, probably we can leave that as an exercise or homework.
Sure.
We can. You get it.
Can you explain me again, like why the C times SK turns into like C plus SK? Can you explain again?
Of what? Of.
The C equals to R plus C.
Yeah, I haven't explained.
Why it turned into.
Okay, just Mark got some idea that why we use addition instead of multiplication.
It's not the same.
Someone
Yeah.
has this idea. What happens if we change it? Now we are analyzing why is a problem.
Yeah.
If
Why
we
is the
change it.
problem?
Okay.
Because
Okay.
it's still complete, right?
I have a tag.
Okay. You got it too?
I got
Okay, good.
So, if this is a prover.
Okay, just write the instance here, right?
Okay.
Approver and verifier,
This
right?
is a
Approver. Okay.
And this is a verifier. The dangerous way is the provers directly send the security key to the verifier. This is bad, right?
Yes.
So I will prove this condition, this situation is the same with this.
It's actually not the same.
So I'll show because the first the provers and verifier are and the at the last at the end is the protocol and the verifier will get this. So if the verifier try to prove to another verifier, and another verifier, the verifier can send the same R because they know the R, the first prover, and another verifier can send a C prime, and finally the verifier the verifier can send this. So the verifier can convince the another verifier this proof is correct. So you can check this proof is the same with this. The verifier will check this proof with proof equal R. Okay, let's see prime. So I think this is the type.
Okay, it's man in the middle, right?
Yeah. Does it
Okay,
make
yeah.
sense?
Okay, I need more time to understand.
Yeah, but that's not like R times K times G to the C prime is not under capital set. No?
You mean this is unknown?
No, like the whole thing that you're saying, the last message, has to be under capital set.
Equals.
Yes, yeah. Yeah, minus set. Like I think this thing of using the capitals and the capitals is a good idea, yeah. Unboxed set.
We can.
No, must be the like the last formula is the unboxed set. Is that the unboxed set?
老师，我刚才想到好像可以伪装就是伪造把那个 R 给那个正确性给破坏掉。就如果说我那边
Okay, just
Okay. You first.
you first. You got the answer, right? You got the answer too, right?
Sorry.
You got the answer. You raise your hand.
Yeah.
Okay. One by one. Don't worry. No hurry. We can write the equation here so everybody can verify.
就是
The prover what's the first step, second step, and the third step of what the prover would do.
这个 R 可以假设成 message。
Yeah, anything. Yeah.
If the R is the like hashed message, then the prover then the verifier at the first time he give the 1C. If use the R plus C plus the SK is equal to R plus BC plus public key. So at the second time, the prover maybe use some way, the verifier use some way to get a new C, and the C is equal to C, like submit R or others, and then he if you use this one and and send to the prover, and the prover to get a new to generate a new Z, and after that he can use the how to say, use the new message. The verifier can use the new message to create a fake site, like fake message or a fake site, because their C can be how to say, can be 消除
Cancel out.
Cancel out about the original message.
We cannot see the
Yeah.
triangle, yeah.
什么意思？我用英文解释好像不太懂。
Okay. So, any ideas from two of you?
I think I know. Let me try.
Okay. Okay, one, two. Okay, other three.
For that, I only think about he can protect the private key.
Yeah.
But after you say that another prover, he don't know private key. He can forge a R to pass it. Is that the idea?
Probably, yeah.
I
Will
think
come up.
the first step is he generates a random number.
Yeah. Right now you come up with a attack, right?
Yeah.
Okay.
For prover to fake.
Yeah. Okay, right here and 1, 2, 3. 1.
Okay, so the first step is to generate a random number. Let's say it's
R prime or R star.
R star, and use it to calculate by generator to get a GR star. That's the first step. And the second step is what is this for? This is to let me see. It's actually I write it down with a moment. This is for to fake finally Z to send them, and how do I say it?我把自己绕进去了。
Okay.
Wait a moment, maybe. You go to first.
Okay, so let's set let the A equals Z to the power R. This is like an element in this group. But within this group, we have an inverse number, which is such that inverse time A equal 1. Right?
Okay, yeah.
Which is like if you want to extract it's like Z term Z to the power R inverse, right? So here is the one equal in this diagram is for Z sorry.
Okay, here's the easy
this to SK.
Okay.
SK, which is our like product key, right? And this is SK here, and this will equal G, which is This is the value R we will send to the verifier. And in this formula to verify, we have like we multiply this this value with this value, and since the result is equal to 1, this is always this value, right?
Okay, yes.
The right side is always equal to C to power C, and since C is sent to the prover can just simply send the
C back.
And this is always true, and the prover doesn't need to know the R or the SK. They can just form.
Yes. Yeah. Did you get it?
So basically, no, capital R is the inverse of the.
Yes. So to cancel out. Yeah. So simple. Yeah. And what's your name?
My name is Steve.
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 Very good. Okay. Okay. So first, the capital R, we use the public key, the inversion of public key. So in the future, here we times capital R and the capital K will get a 1, which means that the capital K will be cancelled out, will be 消掉了. So okay, let's move on to the next part. So today is we have already 40 minutes. Come on. Okay, let's remove this part. Okay. Yeah, probably. Okay.
We can turn it around.
Turn it around?
No.
Okay, no. Sorry. And the attack you mentioned actually is a man in the middle. I think a man in the middle is how say it in English? And man in the middle is actually a problem of Schnorr protocol. Yeah. So in practice, Schnorr protocol we should add more protocol inside to protect the man in the middle attack. But a man in the middle is not the case of this protocol. Okay. Oh, thank you all. Okay. Here. Box, I didn't get your idea. Probably you can. We can talk about after class. Okay.
Actually, I don't understand what
Okay, Leo.
No.
Oh, okay, all right. Very good. Okay, the next topic is. Okay, right now we probably get the why here we use multiplication instead of addition to make sure that R and SK are on different dimensions, different directions, right? So to avoid being canceled out. Okay. Yeah, let's move on to the second Schnorr protocol that we introduced yesterday. Hey, where's the blue pen? It's not blue. Yeah, the blue one. Yeah, we can. Here? Okay, thank you. So we just remove this part, right? Okay. It's no problem. Section 2. The Schnorr protocol. with the Peter's command. That is the statement is almost the same. That to protect the privacy, the prover will commit the SK with help with a blinder, a random blinder. The capital K equals to SK semicolon and a blinder. Blinder, let's use another. Let's use a rho, okay? A rho, a Greek letter. So conventionally, we use the Greek letters for blinders here. SK semicolon rho to commit as a public key. Right now, the public key will looks from outside as a random number because we put a random number here. It's from a uniform distribution with, Then the prover will generate two different randomness in the first step. So your first step, R equals to, we have R semicolon R rho, or GR and R rho. Okay. R and R rho randomness. Prover just samples this to write the Bitcoin notation here to say that the two numbers are randomness. So some people ask me about ask me a question that why we have many randomness, some from prover, some from verifier, and some even before the protocol. Okay, those randomness are used differently, in different way, and for different purposes. For prover, sorry.
H is a constant or a generator from another group.
H is okay. You missed the last.
Okay.
Yeah. Yesterday's class. Okay.
So
here H is G and H belong to the group.
Okay.
And G not equal to H. Okay. So GH should be randomly chosen by using a transparent way, or by some trusted third party. Okay, here's the difference. In the last protocol, only R to protect this K. But right now, the P has two witnesses. One is K, another is blinder. And the blinder is also very, very important. If blinder is revealed to the verifier, then K will be the same with the K here, and losing the real knowledge property. So the blinder role is also very important. So prover cannot reveal the to verifier. So we should protect the rule also. So that's the reason why the prover as the first step should generate two randomness number. R and R rho. R is for SK and R rho is for rho. Protect them. Or we can say as two different symmetric key to encrypt SK and the rho, respectively. Okay, at the second step, the verifier challenges small c. Okay, small c. C is onto, okay. And the prover, as the third step, prover will generate two encrypted data, Z and 0. Z and 0. Here's the definition. Z equals to, as it is in this protocol, R plus C times SK. And 0 equals to R rho plus C times rho. Okay. The witness. So now Z and 0 are encrypted witness. So now it's safe to send them to verifier. Z and 0. The verifier will, just verify Z and 0 homomorphically, as it is in the protocol. Okay. So now we have two equations, two verifying equations. Okay, this is just the one. Okay, one equation. Here we have two equations actually. One is the GZ if equals to R times, only one equation, so I made a mistake. GZ times H0 if it equals to R times K to C. Almost similar. So that's GZ. Okay, it looks like the protocol on the right is two parallel protocol. Each of those looks similar to the protocol on the left, right? I can draw the table here. So in this protocol, the prover wants to prove SK. So in the first step, generate an R, and the third step, generate a Z, right? But here we have a two column table. Okay, this is committed to R, committed to K, committed to R, committed to GZ, right? Here we have a two column table. Got SK and a blinder row, and we'll commit the first row into capital K. And at the first step, the prover generates two randomness for encryption. So we got R for R2. So we commit one row to capital R. And the third step, encrypt the data kind of two values, right? We commit it into G to Z times H to 0. Okay, it's a two-dimension map, two-dimension table. So if we see that table horizontally, we just commit each row, right? For each column, the number of columns means that how many witnesses that prover has. Okay, does that make sense?
Is there a reason we call one secret key and the other row? Like it seems like it's just like one secret key that is two-dimensional.
Yeah.
Like what we call like the one on the left, like what is the difference between the secret key and the row? Like semantically, are they different in how they are used, or is just
Okay, the second column is for blinder, for make all the messages looks random.
Yeah.
So the second column is just for random. The first column is actually the actual value to prove.
The public key
Uh-huh.
depends on row as well.
Yeah.
What we are verifying is the public key.
Yeah.
So it's as secret key as the other secret key, the row.
Yeah.
Like I don't see why one is called secret key and why other is blunder. Since they are symmetric, if we flip them, it has the same.
Yeah, we can swipe them. Yeah.
Yeah.
Nothing will happen. Yeah.
Yes.
Yeah. It's equally. It's equal. They're equal. Yeah. So conventionally, we put the blinder randomness on the rightmost column. Yeah. Okay. So any question about the protocol we learned yesterday? We will move on to the third. So I encourage you to write this protocol on paper or something to think it over. Then I will show you the third. So use the same idea to extend the knowledge. For example, here the prover has only one value, one knowledge to prove the ownership, prove he owned the value. But here we actually prover proves two values. What if we extend to, for example, 1 million? But we can. Only if the G is large enough. Okay, we can actually prove a vector of witness. So from that, we can build a very simple storage proof to prove somebody, okay, your data I didn't delete. Okay, you see your data is still safe. Okay, so third one, horizontal. I don't know how to spell that word. Z-O-N, right? Horizontal extension. Okay. Okay, so now witness is K0, K1, K2, blah, 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 all the way to Kn minus 1. So prover has n witness, a vector. Then the prover commit the public input is the D. We use D as data. It's a commitment of data. D equals to capital D. G0 K0 times G1 K1 times G2 to K2 blah 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 to Gn minus 1 Kn minus 1 times H row. Oh, sorry. Sorry. Okay. We still need a row as a blinder to make the commitment random or in uniform distribution. So yeah, the prover right now we write the protocol prover to prove that the prover has the data associated with capital D. Okay. The first step, the prover will generate n plus 1 randomness, R0, R1, plus R minus n minus 1 from the tossing coin. And also R row from some random generator. So calculate the R0, G1, R1, Gn minus 1, Rn minus 1, H, R row. So send the R to the verifier. Okay, the first step. Okay, the first step. The second step is the same. The verifier replies with a challenger C from IP star. And then the probe will send the encrypted data to verifier. So we'll have Z0, Z1, Z2, blah, blah, Zn minus 1, and 0. Sorry, put 0 here. 0. A sample from some uniform distribution. And then send these Z1, Z0, Z1, Z2, blah, 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 to Zn minus 1, 0 to the verifier. And here's the definition of all of the Z's. Zi equals to, Zi equals to Ri plus C times Ki. I belongs to 0 n, and the 0 equals to R row plus C times row.
N minus 1, right?
Yeah, n minus 1, yes. And then verifier will verify that, G0, Z0, G1, Z1, G2, Z2, Gn minus 1, Zn minus 1 times Hz0 if equals to R times K to C. Okay, this is the verification equation. Okay. That's it. Looks quite similar.
I have a question.
Mm-hmm.
Is there any security issue if we don't use H?
Okay, we just go back to we just lose the zero knowledge proof, zero knowledge property.
But if we have a lot of inputs, the verifier.
The problem is that we only use one randomness, right?
But we are using randomness for all of the witness values.
So what was your question?
If we don't use
H,
in that case, the horizontal extension.
Yeah, so what will happen, right?
Yeah.
Okay, it's a protocol without zero knowledge, that's all. So if we don't care about the zero knowledge property, we can use the protocol without H. If we care about the privacy, we add the blinder here.
How can we calculate the witness if there is no H?
Yeah.
Sorry?
How can we calculate the witness? You have to factorize.
Factorize?
On the G, no? You have to do, the logarithm of the G, no?
Okay, all the G0, G1, they are common reference strings that are randomly chosen from G without knowing the relationship between those G's. They should have been transparently set up by the method I mentioned yesterday, called the hashed points.
Yeah, but what we don't understand, if we take out H and rho out of the equation, why there is no zero knowledge? How can the attacker find out the keys?
Because, okay, if I say, okay, this protocol does not have zero knowledge, I cannot prove that. So if you disagree with me, you please construct a simulator for me. So I'll be convinced. So otherwise, I just guess this protocol will lose the zero knowledge property. Because zero knowledge property, the proof of zero knowledge property is existence proof about a simulator. Yeah. anybody can trying to. So if remove that, can we have a simulator to simulate the protocol? Okay, now we just horizontally extend that protocol. So make sure we can have a very naive storage proof. So, okay, what time is it? Oh, it's okay. I really want to put the first protocol. I think we use the half of this whiteboard. This corner, we can quickly show another example which is fun, and we can compare them together as they, this topic of this class. The first protocol is we extend the protocol vertically. Okay, extend not from this one because it's too complicated for you. You need time to understand. So we extend from number 2 protocol to vertically extend the number 2 protocol. Okay. Now the prover has a K0, K1, blah, 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 K minus N minus 1, N values as witness just as this protocol. But the prover commits the data not as a whole. Actually, for example, there's N values from N different files. So we commit them separately. That means the public input, that's witness. The public input actually is D0 equals to G K0 times H rho 0, and D1 equals to GK1 times H rho 1, and blah 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 all the way to Dn minus 1 equals to Gn minus Rn minus 1 and times H rho n minus 1. That's public input. There are n commitments. So we just use a very simple proof to prove the knowledge of n commitments. Okay, let's do it. I'll write the protocol here. It's enough. In the first step, the prover will generate only 2 randomness for protection. R and R rho sample from distribution, uniform distribution. And then send R equals to GR times HR rho. And then the second step, get a C as usual at P star. And then the prover send Z and Z rho. But here's the definition of Z. Okay, Z equals to R plus C times K0 plus C2 square R1 plus C cube R2 all the way to Cn Kn minus 1. And the Z rho equals to R rho plus C times rho 0 plus C square rho 1. Cn times rho n minus 1. Yes. Yeah, so verification step. Verification. Simple. like verify G Z times H0 if it equals to R times, sorry, actually it's D, 0C times D1C squared to Dn minus 1 Cn. Okay, that's it. Okay, we'll call it the vertical extension. Okay. Vertical extension. Okay.
Why would we choose one over the other? Like, or do we do both? Like horizontal extension versus vertical?
Why both?
Would we do both, or?
Yes, will be, but warning, it will be complicated. Yeah, we will not go that direction on this mini course, but we can do that. Yeah.
If we would have to compare them directly, like horizontal versus vertical, I guess, like, would one even time equip, like, are there like trade-offs?
Yeah, yes. Oh, yes, in some, practically, have you ever heard of Nova from Microsoft? The SETI, Serenus SETI. In Nova codebase, it still use the kind of stuff as a polynomial commitments. Part of. Probably Thursday, on Thursday, we will talk about that. We use the bulletproof technique to optimize this stuff to eventually get a simple polynomial commitments. But right now, we just write down these equations. It's not easy. Oh, sorry, not so hard to understand, because if you draw this as a table, just look at this one, yeah. Okay, let's draw that table here. We actually, okay, here we got the table like it's many columns, right? But only 3 rows. K0, K1, K2, Kn minus 1. Here we have R0, R1, R2, Rn minus 1. Sorry, row here. Row. R row. And here Z1, Z2, blah, blah, 2, 0. But for this one, we have multiple rows, 2-column table. Okay. Sorry. K0 row 0, K1 row 0, blah 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 to Kn minus 1 row n minus 1. And here we have R row. We got Z and 0. Right, to commit to D0, D1, Dn minus 1. And here we commit to R, commit to, no commitment. G, Z, 0. Okay. D, R, okay. We can easily combine them together. And we still have such fancy technique to optimize over that naive combination. I think the work, the techniques were very popular probably 15 years ago. So it's old techniques, but still those techniques nowadays can see many different places in modern proving systems. The basic protocol techniques. Okay, I think. Oh, we still have 10 minutes for a question. So quiet.
Still forming.
Okay. Tomorrow could be. Okay, so far the first 4 protocols are only proof of knowledge that you own data of verifier of someone. But tomorrow we're going to prove that okay, we can prove the property of the data. For example, A plus B equals to C. We have 3 commitments. We prove that okay, the values inside the boxes they satisfy the addition and the product relationship. So they'll be closer to polynomial commitments. And if we can have the addition and the product multiplication proofs for the value inside the commitment, then we can prove a circuit naively, because we can commit everywhere in the circuit and verify each gate, because we have only 2 types of gates, additive gate and multiplicative gate. We prove each gate satisfies the operation. That's okay. We will prove successfully the satisfaction of a circuit, but it has very low performance. But we can do it, and tomorrow. Okay. Yeah, I forgot to give some examples today. I think time is probably we can. I can give some example tomorrow, probably before the proving addition. Okay. All right. Thank you very much. Thank you very much. I'm happy so many people can follow. Okay. I hope to see you tomorrow.